Hello everybody, today we're going to have a look at what's known as momentum. So we're going to start with a little question actually. Let's imagine you've got all five of these different types of ball. We've got a table tennis ball, a football, a wrecking ball and an exercise ball. If they're all travelling at the same velocity, which one would be the hardest to stop? Have a little think about this one. Okay, we'll come back to that a little bit later on. You've probably got an idea it's the wrecking ball, but why? So this is what we're going to look at. Why is it more difficult to stop the truck compared to my car when they are travelling at the same velocity? So, what is momentum? So, we've got three definitions here. So, we've got momentum is determined by the mass and velocity of an object, momentum is determined by the size and speed of an object, and momentum is determined by the height and weight of an object. Just have 10 seconds. Which one do you think is true? Which one do you think is the correct definition of momentum? Okay, hopefully we've gone for this one. Momentum is determined by the mass and velocity of an object. So, useful information. Can you think of any scenarios where having loads of momentum would be helpful? So, I'll give you two to start with. We've got a wrecking ball, the higher momentum, the more damage it's going to do. And we've got a rugby player. The bigger they are and faster they are going, the more they're going to run through, the more other players are going to find it difficult to stop their run, to stop their momentum. So, press pause on your worksheet. Press pause on the video, sorry, and complete task one on your worksheet. Rewind to the walkthrough if you need any help. It's nice and easy. Can you think of any examples where momentum is a good thing? Press play when you're ready to continue. So hopefully that clears that up. Now, it's physics. We have got some maths to do, and that's what we're going to do. Now, this part I think is fairly simple, but then when we start looking at it later on in the lesson, it does get a little bit more difficult. So it's really important to follow it step by step. So our calculation for momentum is momentum in kilograms meters per second is equal to the mass in kilograms times velocity in meters per second. That is it. It is a simple equation. Momentum equals mass times velocity. Remember, our units must be in these, otherwise your answers will be wrong. You'll be out by certain magnitudes. So for example, let's calculate the momentum of a sprinter of mass 50 kilograms running at a velocity of 10 meters per second. So, as we've done before, the first thing we do is we write down our equation. Momentum equals mass times velocity. Again, we've highlighted the different colours. So do I need to alter the formula? Well, no, because the question's asking me to calculate the momentum. Momentum equals mass times velocity. We've got mass, 50 kilograms. We've got velocity, 10 meters per second. Let's plug our numbers in. 50 kilograms times 10 meters per second gives us a momentum of 500 kilograms meters per second. Nice and easy. Let's do another one. So another sprinter has a momentum of 750 kilograms meters per second, running at a velocity of 10 meters per second. What is her mass? So we need to do something slightly different. So again, let's put our equation in. This is the one we're going to use. Momentum is equal to mass times velocity. Do we need to alter the formula? Yes, we do, because the question's clearly asking us for the mass. So we need to make mass the subject of our formula, which gives us momentum divided by velocity is equal to mass. Once you've got your formula, we'll plug our numbers in, and so therefore we should have 750 kilograms meters per second divided by 10 gives a mass of 75 kilograms. Go through the same process every time. Write down the formula. Do you need to rearrange it? If so, rearrange it, and then plug your numbers in. It is nice and easy. So here's your first task. To start with, I've colour-coded everything, so blue for mass, green for velocity. Notice the units. This is how you find out which one you need. Okay, I'd like you to work through all of them that are on your worksheet. So what I'd like you to do is press pause and complete task 2 on your worksheet. Rewind to the 2 examples if you need any help. Press play when you're ready to go. So, next task. We've done the maths. We've picked out what we need to do. Let's make it a little bit more complicated. Let's look at it in terms of how to answer exam questions, because ultimately this is what you need to do. So, press pause and complete task 3 on your worksheet, and rewind to the walkthroughs if you need any help. Again, pick out the information you need, plug it into the formula that you need to use, and solve. Go through this process, these step-by-step ways every single time. Press pause on your video and press play when you're ready to go. So now we're going to expand on it a little bit. We've done the sort of fairly easy part of it. Now we're going to look at what we know as the conservation of momentum. So to understand and calculate conservation of momentum during an explosion is one of the things you may be asked to do in your exams. So let's work through it. So if two objects collide or interact, the forces acting on each one will be the same size but in opposite directions. Now the same is true for the change in momentum of each object. It's a lot like the conservation of energy. What goes in has to come out. It has to be the same. So it means that the momentum lost by one of the objects will be gained by the other object. Therefore, whenever two objects collide or interact, momentum is conserved. So if we look at this in terms of ice skaters pushing away from each other, they both push away from each other force, and they will both move on. Now, we're going to use the calculation there, P equals M times V, which is your momentum calculation, P being momentum, to calculate momentum during explosive interactions. That's what we're going to work on today, looking at different examples of how to use that formula and expand on it to prove the conservation of momentum. So, momentum before must equal momentum after. It cannot change. Again, it's like the conservation of energy. What goes in must come out. Momentum must stay the same. As long as no external forces are acting on objects involved, the total momentum stays the same as in explosions and collisions. We say that momentum is conserved. You can use this idea to work out the mass, velocity, or momentum of any object in an explosion or collision. However, during a collision, momentum may not always be conserved, as there may be an external force acting on the colliding objects. Now, for the purpose of this, we're going to assume that those external forces aren't there. So, let's look at the equation again. Momentum, P, the unit is kilograms meters per second. P comes from the Latin for impetus, which is another Latin word to describe momentum. I can't remember what the P actually stands for, but that's where it comes from. We've got mass, kilograms, velocity, meters per second, and we've put this into a nice convenient formula triangle for you. Again, I'm not keen on them, however, you can go back to this if you need to use it later on. So, conservation of momentum, we're going to put some maths to it. So we're going to work through this. Bear with me, go step by step. It might be worth you actually writing this down as I go through it to help you familiarise yourself with it in the process that we need to do. So, in the below question, two cars collide together. The grey sports car collides into the back of the green family car, and let's say it sticks to it because there's no elastic in the collision. It's what we call an inelastic collision. What do you think will happen to the speed? And can you explain why using the idea of conservation of momentum? So, there we go. We've got our green sports car, our green family car, sorry. It's got a speed of 0 meters per second. It's got a mass of 800 kilograms. And here's our sports car. It's got a speed of 50 meters per second. It's got a mass of 1,000 kilograms. So what we need to do, there we go. There's our crash. What's the new speed? We know that because it's hit this car in front, we know it's going to be less than 50 meters per second. That's common sense. We can see that. You hit a stationary object at a certain speed, you're either going to stop or you're going to slow down. That is common sense. But we can use maths to work out how fast. Now, all we do is we look at it before the crash and we look at it after the crash. Before the crash, we've got a 1,000 kilogram car, we've got an 800 kilogram car. After the crash, we've got two cars stuck together, so we add the masses together, 1,800 kilograms. But we don't know how fast it's going. So let's work it through. So we'll divide this calculation into two separate parts. Total momentum before the collision and momentum after the collision. So let's work it through. Momentum, remember, is P is equal to car 1 plus car 2. So momentum of car 1, we're going to use our formula. Momentum equals mass times velocity is 1,000 kilograms times 50 meters per second. So the momentum of car 1 is 50,000 kilograms meters per second. Now, momentum of car 2 will be 0. You may ask why? Well, that's because it's not moving. Anything times 0 will always be 0. So the total momentum is 50,000 kilograms meters per second. So the rule of momentum tells us after the collision, the total momentum must be 50,000 kilograms meters per second. What happens on one side has to happen on the other. So therefore, mass times velocity equals 50,000 kilograms meters per second. But we've got a new mass because our cars have joined together. And our new mass, remember, is 1,800 kilograms. Car 1 was 1,000 kilograms, car 2 was 800 kilograms. So how can we calculate the velocity of the two cars that are now stuck together? Well, we just use the equation. 50,000 divided by 1,800 gives us a velocity of 27.8 meters per second. And that is it. Let's go back. That is it. All we do, we solve one side, then we take that one side and move it across to the other side, use our new figures to solve our second part of the equation. It is nice and easy, but we must follow these steps to work out what happened, what the total momentum was before the crash, and then we work out the momentum after the crash. So let's go through another example. A railway engine of mass 800 kilograms is travelling at 5 meters per second, collides with and becomes attached to a truck of mass 200 kilograms travelling at 2 meters per second. Calculate the speed of the truck and the engine after the collision. So we're going to work through it. Step 1. Remember, the momentum before the crash must equal the momentum after the crash. So let's work it out before. So we have got 800 kilograms times 5. There we go. Momentum of train 1, 800 kilograms times 5, plus 200 times 2. And there we go. Second part of the train, 200 times 2, gives us our total momentum before the crash, 4,400 kilograms per meter, kilograms meters per second. Remember our units? There we go, kilograms meters per second. So step 3, therefore momentum after the crash must equal 4,400 kilograms meters per second. This is the conservation of momentum. What it is before the crash has to be the same after the crash. So let's rearrange our equation. So we've got our new momentum 4,400. We're going to use our equation velocity equals momentum divided by mass. Remember, we've just rearranged this one here. Plug our numbers in. Sorry, the numbers have gone out of order. So step 4, total mass is 800 plus 200 because our 800 train plus 200 train gives me a total mass of 1,000. So plug our numbers in. New momentum after the crash, 4,400. This time we're going to divide it by 1,000 because that's our new mass. That gives us 4.4 meters per second. Again, it is nice and easy. We must step through. Let's go back. So momentum before must equal momentum after. Work out the momentum before by adding together the individual momentums of the two items in the crash. Move that across because the momentum there has to be the same on both sides. And we've got a new mass, which we plug into our equation, gives us 4,400, in this case, 4,400 divided by 1,000, 4.4. So I'd like you to have a go at this now. We've broken it down a little bit into step by step. So what I want you to do, we've got two lorries. One's got a mass of 20,000 kilograms and a speed of 14 meters per second. The other one's got a mass of 30,000 kilograms and a speed of 20 meters per second. So nicely step by step through for you. Calculate the momentum of lorry A as it travels along the motorway. Calculate the momentum of lorry B as it travels along the motorway. Lorry B collides with lorry A and they stick together. Calculate the velocity of these lorries immediately after the collision. So press pause on the video and complete task 4. If you're finding this difficult, go back to the walkthroughs that we've just done. Go through it step by step. Once you've had a go at it, press play. So we're going to have another go now, but we're going to take it in a more exam style. So task 5, highlight the important information in the diagram. Use the equation to help you identify the information that is present. So here's our equation. You know the units of momentum. You know it's kilograms meters per second. We can use that to help us for our equation. Two railway carriages collide and move off together. Carriage A has a mass of 12,000 kilograms and it moves at 5 meters per second before the collision. Carriage B has a mass of 8,000 kilograms and is stationary before the collision. What is the velocity of the two carriages after the collision? I'd like to solve that one, please. So press pause on the video and complete task 5. If you're finding it difficult, again, go back to the examples with the cars that we did earlier. It is nice and easy. So now we're going to look at it in terms of explosions. So when you fire a rifle, the explosion causes the bullet to fly out of the barrel. It also causes the rifle to push back into your shoulder. We know this is recoil, those of you who have fired weapons in the past at cadets. So there we go, we've got a man and his little air rifle. Even that will have a slight amount of recoil. So the velocity of a bullet can be calculated using the equation, again, P is equal to mv. Let's expand it. Momentum is equal to mass times velocity. So a bullet of mass 0.01 kilograms is fired from a rifle of mass 2 kilograms, which recoils with the velocity of 1 meter per second. What is the velocity of the bullet? Now we're going to do exactly the same thing again. Momentum of the bullet will equal to the momentum of the rifle. So let's go through it. Let's calculate the momentum of the rifle because you've been given its mass and velocity. So back to our information. Bullet of mass 0.01 kilograms is fired from a rifle of mass 2 kilograms, which recoils at a velocity of 1 meter per second. Let's go through it. Velocity of the rifle is 2 times 1, 2 kilograms meters per second. So those are 2, those are 1. So we can calculate the mass and the momentum of the rifle. What happens on one side must happen on the other. So let's apply the rule of conservation of momentum. Momentum of the rifle has to equal the momentum of the bullet. All we've done here is we've expanded it, m times v, m times v, what's called substitution in our equations. So therefore, the momentum of the bullet must be equal to 2 kilograms meters per second. 2 kilograms meters per second for the rifle. This side has got to equal 2 kilograms meters per second. So let's rearrange our momentum equation. Find velocity. Velocity is equal to momentum divided by mass. So 2 divided by 0.01 is equal to 200 meters per second. That's how fast our bullet is going. So press pause on the video to complete the next task. If you find it difficult, again, go back to this walkthrough. It's very similar. It was just going to give it some real life context rather than just looking at maths. So why does a cannon recoil when it's fired? Well, we've got a little video clip you can watch here. You're going to click on it, have a look at it. I apologise to the guy, he's very dry in his delivery. However, it is packed full of information and it goes through the maths with you again. So now we're going to look at it in terms of the conservation of momentum, but we're going to look at it in terms of vehicles travelling in the opposite directions. This is taking it another level. So let's say we've got 2 cars and they have a head-on collision. Trolley A has a mass of 3 kilograms, a velocity of 8 meters per second, and its momentum is 24 kilograms meters per second, because it's 3 times 8. Now, here's the important thing. Trolley B has a mass of 5 kilograms, but its velocity is minus 4 meters per second. You might ask yourself, why is it negative? That's because it's travelling in the opposite direction. Trolley A. One has to be the positive. Remember, velocity is a magnitude and the direction. A is positive that way. B must be negative this way. So it gives us a momentum of minus 20 kilograms meters per second. So it's 5 in our mass times minus 4. Remember, the minus is giving you an indication of the direction. If this trolley A is travelling north with 8 meters per second, this trolley will be travelling south at 4 meters per second. The minus is showing it's travelling in completely the opposite direction to the bullet. So the total momentum before the collision, we add them up, 24 plus minus 20 gives you 4 kilograms meters per second. Mass after the collision is 8 kilograms. 3 kilograms plus 5 kilograms. This part isn't minus, it's only the velocity. So the momentum after the collision must equal 4 kilograms meters per second. As we've already worked out, 24 plus minus 20, 4 kilograms meters per second. And all we need to do is do a little formula rearrange. So the velocity after the collision will be the momentum by the mass. Momentum is 4 divided by mass, which is 8, gives you 0.5 meters per second. Because there is no minus, it will be 0.5 meters per second in the eastern direction. If there was a minus in front of it, so press pause, complete the extension task that's there for you. It's entirely up to you if you have a go. This does take it to the extreme next level where we start to really look into velocity. It's quite interesting. On the next 3 slides after this, that's on your power pack, there are some interactives. It might be a good idea for you to have a look at them. It looks at it in terms of explosions, because we can take velocity in different directions, so how it will cancel each other out. And there is an interactive that you can use where you can crash these little trolleys into each other at various speeds and various different velocities, with various different masses to see what happens to momentum. Okay, so here's one of them, another, and the other. Have a look through it. They may work, they may not. It's very old technology, but it can be quite useful. So that sort of concludes today's lesson on momentum. We are going to expand on it next lesson and look at linking different equations to momentum, including Newton's second law, which is force equals mass times acceleration. As ever, if you need any help, please don't hesitate. Give me a shout via email or on the chat page. And some of you have also requested the virtual face-to-face meeting this weekend. Please don't be shy if you want to have a chat about any of the physics and things like that, or any of the other work that's been set for you in science. The next time there is one, please don't hesitate to get in touch. Thanks, guys. I hope you enjoy it. Have fun.